Hello, my friends of Hatari Labs. Welcome to this tutorial. This tutorial is an example problem of modeling of a groundwater model flow with Model Muse. Okay, in this time, this is an adaptation from a problem that is on the MODFLOW documentation. Yeah, this is the when you try to install MODFLOW. Actually, this is the last. I think this is page 224 from the paper from the MODFLOW paper, and here we are going to deal with a 5-layer aquifer, or like a setup of 5 aquifers, where the first aquifer is unconfined. This one is modeled as an aquitard. And then we will discuss what is an aquitard, and this is as well a confined aquifer, another aquitard, and a confined aquifer. Then there is a constant head at one side of the model, and there is a drain, and as well there is recharge. If you see that the original problem is in feet per second. Feet is the unit of length, but in our adaptation we will use the international system, so we will work in meters and seconds. Okay, so far we are going to start the modeling. Why not? Okay, we start by opening a new Model Muse. Okay, we will create a new MODFLOW model. Okay, next. We have to declare anything here, so it doesn't matter because it's just declarative. Okay, and here we are going to wait for me a little bit. Okay, we will assign the number of column rows, and as well the column width and the column row. Let me wait for me. Okay. So we are going to have 15 columns times 15 rows, and the column width will be 5,000, as well the row width will be 5,000. We will deal with 5 layers, and this will be upper aquifer, this will be the lower aquifer. Okay. Let's see, I will change, because in Model Muse you cannot have 2 layers with the same name. So like I cannot do a copy. Okay, so I can do lower, I have to do a similar name but not exactly the same name. Lower aquifer. Here is lower confining area. Confining layer. Lower aquitards, yeah? This is middle aquifer. This is the upper aquitard. And then this is the upper aquifer. So we are dealing with the upper aquifer, upper aquitard, middle aquifer, lower aquitard, and lower aquifer. Okay? So here is 200. Here is minus 150. This is minus 200. minus 300 minus 350, and this is minus 450. Okay, cool. So here we have 200 minus 150 minus 200 minus 300 minus 350 and 450. Okay, so if we have this remember that in MODFLOW you do not specify the aquifer thickness. You rather than specify the top and the bottom of each layer. So that's why the upper aquifer will be from 200 to minus 150. So it will actually have 350 meters thick. Okay, and the upper aquitar will be from minus 150 to minus 200. It will have 50 meters thick. Okay, so we go to finish, and this is our aquifer. Okay, isn't that great? Okay, cool. Then we go to MODFLOW layer groups. Okay, first we expand, and then with this we center. Okay, and then we go to MODFLOW layer groups, and then we see that the upper aquifer will be non-simulated and the lower aquifer will be non-simulated as well. And what does it mean to be non-simulated? It doesn't mean that there is no flow on this, that these aquifers are not in the system. Yeah. What does it mean is that actually the aquifers have really low hydraulic conductivity. So this hydraulic conductivity is so low that flow on the horizontal direction is negligible. It's so low. Yeah? So if it is so low, like the only groundwater flow that can happen in these aquitards is just flow through, vertical flow that goes across the layer, okay, perpendicular to the layer, and that is what it means non-simulated. Non-simulated is actually that the horizontal flow is not simulated, but it allows the vertical flow. Okay, cool. Do you understood? I hope. Okay. Okay, great. Then we are going to assign. So then we are going to assign. We create. Okay. Then we are going to assign some hydraulic conductivities for every layer. Remember that this layer is an aquifer, this is an aquifer. Yeah, there is a non-automatic way to apply hydraulic conductivities to each layer. So it will be edit data sets, required hydrology kx, okay, and then we say edit formula, and then we go to functions, logical, and then we set case. Yeah, what do we have done? We have come to data, edit data sets, required hydrology kx, and here in edit formula, data required hydrology, functions, logical case. So case is actually in Python will be a switch, I guess, or maybe. Okay, so it will be a logical that for every index it will apply a different value. So, but our index in fact will be layer. So what does it mean? That for every layer it will apply a different kx value. Okay, remember that in case of layer 2 and layer 4, it doesn't matter which layer do you have or which value do you have, because actually flow in the horizontal direction is negligible. Okay, so here 0.001. Here I put a 1000 because this will be actually for layer 2. So it's a value that is not relevant. I mean, it's a value that actually won't be applied to the model. And here is 0.001. And this as well, because this is layer 1, layer 2, the first aquifer, middle aquifer, then the second aquifer will be as well 1000, and this will be 0.002. I put a really strong value, I mean a really high value in order to emphasize that this value is not applied. No? Okay, because if you have this on your numerical model, like you will have for people that deal with this, you never have a conductivity of 1000 meters per second. I mean, it won't reflect the turbulent flow. Okay, it will reflect turbulent flow conditions. Okay, so this is okay. So this is okay. By default, ky is the same as kx, and kz will have another values. Why it will have another values? Because this formula as well, logical case. Yeah. Here will be case layer, and for the first it will be 1, or it could be 1000, whatever you want. It will be 1. And then the next one will be 1 10 to the minus 6, because this is actually the one that is going to work, because flow goes just through, I mean, flow is perpendicular to the plane for layer 2 and layer 6. This is 1 as well, 1 10 to the minus 7. Okay, cool, and this is 1. Okay, so this is 1 10 to the minus 6, 1 5 10 to the minus 6, and 1. Okay, cool. Then we say okay. Okay, so this one will apply our kz, and this one will apply our kx, and ky is the same as kx. Most flow initial head, I mean, you are dealing with confined conditions, but in any case, I mean, it really doesn't matter. Your model won't be dry, but if you put edit formula, you can set up this as model top. Why not? Okay, in this formula you go down and model top. Okay, great, cool. Then we put apply and then close. Okay, great. Please save your project. File, save. And then we say, we create a documents, a new, that will be example problem or MODFLOW with Model Muse. Yep. And here I create a model. And then here it will be model 1. Cool, great, you are doing excellent. Okay, then we go to model, then we go to time, and on time we are going to change it. The default values are from 0 to 1, minus 1 to 0, but for our case we are going to deal with the number of seconds of 1 day. So it's from 0 to 80, 100, 500. Okay, and then we are going to analyze every just 1 day. Okay, I mean, this is a steady state, and then we are not going to split. We are going to split the day in just one time step. Okay, because it's a steady state. Okay, if you are dealing with transient, maybe it would be worth it to maybe upon the boundary conditions that you will give to your model, you can evaluate this every half an hour, or maybe every hour, or maybe every 2 hours. It really depends on you. Okay, we said okay, and then we go to model, and then we go to MODFLOW package and programs. And here on boundary conditions, we are going to apply CHD, that is for the regional flow, recharge. We are going to set some wells, and we are going to apply a drain package. Okay, as well here it is LPF. Okay, because it's layer property flow, that is the default flow package of MODFLOW. So once again, CHD, recharge, well, and drainage. Okay. 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 So we say that as okay. And then we create an object with this one. We create an object. Okay. And this object will be, yeah, and this object will be from here to here. Remember that this has to be not on the side of the cell, but it has to be through the center of the cell, because what you will define is boundary conditions that on the cell where this object is on the intersection of this object with the grid. I mean, it will apply on the cell. It won't be applied on the border. Okay, so that is why it's very important to set up this on the center of the cell. Okay, and this will be how it will be head 0, because it actually represents the sea, so it's actually at 0 meters above sea level. Okay, set value of intersected cells, and this has two, that is from model top edit F middle aquifer bottom. Okay, so in this case it's model top to middle aquifer bottom. Yeah, head 0 down. Okay, great. So then we go to MODFLOW features, then we go to CHD. We start from 0, we end up on 8,400, and then this is 0, and this is 0. Okay. Okay. So once again, 0, set value of intersected cells, model top, middle aquifer bottom, CHD, 0 term, and the head is because it's sea level, so it's okay. Then we are going to apply the recharge. The recharge will be located by using this or this. In this case, we are going to use this. So we create an object that actually goes through, that covers the whole model. Yeah, okay, here. And this will be recarga, recharge. Okay. Set value of enclosed cells, this will be have zero formulas, set value of enclosed cells, 0 formulas. Okay, this is recharge. And then we go to MODFLOW features, and then we make check on recharge. Okay, this will be from 0 to, and the recharge rate will be 310 to the minus 8. Yeah, because we are dealing with meters and seconds, and this is the recharge rate maybe of 100 millimeters per year. Yeah, but in meters per second, this is the rate. Okay, it's so small, but do not worry about, because MODFLOW deals well with this type of rates. I mean, it could be seen small, but in a year it's not so small. Okay. Okay, great. You are doing excellent. Okay. Then we are going to define some wells. Yeah, we are going to define some 12 wells in layer 1, 2 wells on layer 3, and 1 well on layer 5. So then we apply this one. First we go to object and then hide all objects. Object, hide all objects. And then we go to here, please check here, we are going to column 8, row 9. Column 8, row 9. Column 8, row 9. Here. And this will be well 1, layer 1. Yeah. This will be the first layer of the first well of layer 1. Okay. And if you have seen, we have to, I mean, the model requires us to do 12 wells. So we are not going to define 12 objects. So there is a better way to do it. So this is model top after aquifer bottom because it will be on the first layer. Yeah. And then we go to MODFLOW features, well, direct from 0, and the pumping will be -5. Yeah, remember that the discretization is 5 kilometers times 5 kilometers. So this -5 is not actually one well because there is no well that can pump 5 cubic meters per second, but it's rather the representation of a field of wells. Okay. Okay. Then then we can change of color here. We can do a change of color. Okay, then we go from, then in order to duplicate this, we create, and then we go to add point sections, And here I'm going to press, I guess, well, here, and sorry. I'm pressing Control Z. Okay, here. Okay, so I just press this one. Okay. So here, or do I press Control Z and this the same? Okay. So because I have done this, but here there are no, all the ones are here. If you see here, there is all the wells that are on layer 1. Okay. If you want to see if you want to check, if you want to do another check, you can go here. You can do boundary conditions, well pumping rate. Okay, cool. So this is the pumping rate. No? Then we are going to create the wells on layer 4, the middle aquifer. So this one is the middle aquifer. Okay, so is this one, look, is this one. Okay, so here object, hide all objects, and here we are going to define one well. So here we go with this one, and then we go to column 6, okay, column 6, layer 4, okay, this one, column 6, layer row 4, column 6, row 4, and this will be called well 1, and this will be layer 3, okay, and it will be from the upper aquifer to the middle aquifer bottom, okay. Then we go to wells, then we go to direct, and then it will be from 0 to, and this is -5. From 0 to 10, and this is -5, and this is direct, and this is well, okay. Okay. And then again we go to object, and then we go to add point sections, and we create another here. Okay, that's right. So we have created the two aquifers from the second layer. So we go to date object, hide all objects, and then we go to the last, and then we will create another one that is the same characteristics, column 11, row 5. Column 11, row 5. And this will be well 1 layer. We can change the color, don't worry. This is from lower aquifer bottom to lower aquifer bottom. And here is another well that is as well direct, that goes from 0 to the end, and then pumping rate is -5. -5 because it's pumping. Okay, and let me check. Yeah, this is -5. This is -5. And those are -5. Okay, that's great. Okay, then we are going to use another capability of Model Muse, and this capability is the one that we can import some drainage, but as another look. We can import those drainage, but as a special notation. You will see how. Okay. On the description of this project, of this model, you will find you will find this text file. You open with Notepad, yeah, and this is actually this. Do you see? This is actually all of these commands, but all of these commands are actually can be understood by MODFLOW. Okay, this can be understood by MODFLOW. So I just select, I just go to File, select all. Okay, File, copy, and then paste. And automatically it appears this drain with the whole characteristics, because it's actually this has the setup to define this sequence of drains. Okay, it is being here. Okay, so do you see that these are the drains? So if I open one here, I will see that this goes from here to here, and it will a drain, as well as it will be this, and so on. Okay, so it is there. Okay, That's okay. Please save your project, and then go to MODFLOW Package and Programs. And then on solvers, we are going to deal with the zip, yeah? That is an solver. The most common are PCG, zip, and then MODFLOW NWT. Okay, so then we go to max ether. It will be 550. IP calc will be 0. And we sit will be 0.01. Yeah, if you wonder about these values, I strongly recommend that you read the papers and the manuals, because it will, in the papers and the manuals, it actually will specify all the configuration, because you do not have only one solver, you have many solvers, so you have to look, and you have to assess which of these are more appropriate for you. As I have said you, the zip and the PCG are the most common when you are dealing with MODFLOW 2005, but you are also welcome to use MODFLOW NWT. Okay, great. Then we save it again, and then we run the model. Okay, with this we run the model. Okay, model. I haven't updated, but there is no problem. It can run like this, and it appears this one. When it appears this, it means that the model has run okay, that there is no warnings, and then the percent discrepancy is okay, and you have reached the convergence of the model. So that many things, many good things are happening here. Okay. First of all, if we close this window, it will appear sorry, again, I run it again. Okay. Okay, it will appear this. Okay, so if I go to the bottom, it will be, we will have the water budget, the volumetric water budget. Okay, so this is the volumetric water budget, and these are the rates. Okay, so the recharge is the main input to the system, that is 157, where from this recharge, the constant head, the recharge is the main input, where the constant head is taking 58 cubic meters per second. Okay, that is what the water that goes to the sea, whereas the wells takes the 75 liters per second. That is, this whole set of wells at different depths are the ones that they have this 75, and the drainage is taking 23 cubic meters per second. Okay, and the discrepancy is almost 0. Okay, then we go, okay, then we close here, and then with this we import, with this we will import the results of the model, and this will be the FHD, this will be the FHD, this will be as control grid, okay, we put okay, and this is the representation, yeah, of the hydraulic heads on the extension of the model. Okay, this is the representation on the aquitar. This is the middle aquifer, and it appears this and this because these are the wells that are located on the middle aquifer, and on the lower aquifer there is a well. This one is the well that is located in the lower aquifer. Okay, so this is mostly the tutorial, yeah, and I hope that you have found this tutorial very interesting and very basic, because the purpose of this tutorial is actually to give you an input, an overview of what you can model with MODFLOW, okay, and Model Muse, okay. So you will find this model as well as the input files on the description of the model. And we hope we are from Hatari Labs. Hatari Labs is blogs in numerical modeling of water resources with open source software. And we hope that you can follow us by our channel on YouTube and as well as our social networks. Okay, please do give a like to this video, and we hope to see you in another tutorials. Okay, see you. Bye bye. Bye.